All right, thank you very much. Thank you, Jean-Daniel, for the introduction, and thanks a lot for inviting me to speak. So my name is Steve Oudot, and today I want to talk about topological graph structures and their use in data analysis. So the content of the talk is a little bit ambitious considering the time allotted to it. So I will be mainly talking about structure and stability properties, and if I have some time, I'll say a few words about statistical results. As a rule of thumb, what you can consider is that what Bertrand was presenting earlier this morning about statistics on persistence diagrams, basically you can do the same on these topological graphs. So graph structures are ubiquitous in data sciences. First of all, because you can see them in many types of data, such as, for instance, like proteins or social networks or astrophysical data. But also, they are a tool of choice for performing the analysis, for the analysis pipeline itself. First of all, because they can be easy to compute, small to store, and also because a graph can always be embedded in 3D, so you can actually see your object, versus like higher dimensional complexes that might be more difficult to visualize. These graphs can encode various types of information about the data. For instance, they can encode statistical information or geometric information or a topological type of information. Or it can be a combination of those. So today I will be mostly interested in these so-called topological graphs, which encode information about the topology of the structure underlying the data. So what is the idea? So you start from your favorite data set, and what you do is you choose a function from that data set, which we call a lens or a filter. And that function is basically, has a codomain being usually R, but it can be also R to the K or some more general metric space. And then you use this function to kind of slice your data and get an understanding of how the data are positioned with respect to the levels of that function. So let me make this a little bit more precise mathematically. So the kind of canonical mathematical object to do this is called the Reb graph. It was introduced by Reb in the 1940s. And it works as follows. So you start from, forget about the data, just take a topological space here, which I call X, and choose a function on that space, a real valued function. And the graph is defined as follows. So you take the fibers of the function, namely the preimages of the singletons here. So here is, for instance, for this particular singleton, here is the corresponding preimage. And what we're interested in is the path-connected components in that fiber. Okay, so I call them A, B, and C respectively. And then each path-connected component is going to be represented as a point in the graph. And then you basically extrude this information throughout the value of the singleton here. So the precise definition is through a quotient. So 2 points in the space are equivalent if and only if they lie in the same fiber, and more precisely if they lie in the same connected component of that fiber. Okay? And then you take the quotient of your space by this relation. Now this relation is nice because the function goes to the quotient, and so you get a real valued function on this Reb graph. So you can represent the Reb graph on the same functional ladder as the functional scale as the original space. So this is an example of a space and its corresponding graph. And under some sufficient regularity conditions on the space and the function, you are ensured that the graph is actually a graph. It's a one-dimensional stratified space. Okay. So this object has been used like for a while in computer science. Its main use is in scientific visualization. So as I said earlier, it's very easy to visualize a graph because you can always generically embed it in 3D. It's been used also a lot in computer graphics and computer vision because it's useful for doing skeletonization of objects. And so then you can use these skeleta to parameterize the physical objects you want to work with. And via these parameterizations, then you can easily perform data comparison, segmentation, matching, or you can transfer properties from one object to the other, and so on. So there's a whole lot of applications of these graphs. Now, in all these applications, one very important operation we want to make is to be able to compare the Reb graphs. Okay, if you give me two Reb graphs, I should be able to tell you what is the distance between these two red graphs, or to what extent do these red graphs differ to from each other. So for this, we need to introduce a metric between red graphs. And one very natural way to do it is to see red graphs themselves as metric spaces. So how do you define a metric on a red graph particularly? Well, here is one possible way. So for every pair of points x and y, you consider all the possible paths, continuous paths from x to y in the graph, so which are represented by this notation here. And for every such path, you measure how high it goes in terms of function value and how low it goes in terms of function value. So you take the maximum and the minimum of the values of the function taken over the path, and you take the difference of these two. And now you minimize over all the possible choices of paths. Okay? So this is an intrinsic definition of this is an intrinsic metric. And now, once your red graphs themselves are equipped with metrics, then you can compare them using standard tools, in particular the Gromov-Hausdorff distance, assuming the red graphs are compact. And here is the definition. So the Gromov-Hausdorff distance, if you have two red graphs like the ones here at the top, you basically try to align these two graphs together. So for this, in this example, I took this one and I aligned it as best as possible with the one on the left. And then you just take the standard Hausdorff distance between the aligned graphs. Okay? So mathematically, this is written as an infimum over all possible joint embeddings, isometric embeddings of the two graphs into a same space. And the quantity we're taking the infimum over is this. The quantity we're minimizing, is the Hausdorff distance in the target space, in the ambient space. Okay, so this is all nice mathematically, but it's very hard to compute in practice. In particular, even if you consider very simple, like even though the red graphs themselves and their assumptions are simple because they are graphs, it leads to NP-hard problems to evaluate exactly this distance. Okay, even approximating it can be complicated. So there's a result by Agarwal and co-authors from 2015 that says that even in the very specific case where the graphs are just trees, then it's NP-hard to compute this distance. Okay? So we need to do something if we want to be able to evaluate it in applications. So there's a number of suggestions that have been made. So the very first one dates back to Gromov's work from the early 80s on intrinsic metric spaces, where he proposed to change the definition of this Gromov-Hausdorff distance by using what he called correspondences. So the idea here is, I'm not going to go through the details, but the idea is that instead of looking at every possible ambient space and joint embeddings in that space, we're going to force the ambient space to be the product of the two red graphs. Okay? So then the question it becomes how each of the original red graphs are going to embed into this product space. And then this definition has been refined in the particular case of red graphs by Bauer et al. A few years ago, where they considered that instead of taking any possible embeddings of the red graphs into the product space, you would take embeddings that are given by continuous maps from one graph to the other. So this reduces the space of embeddings in which you want to look for you want to minimize this quantity here. And then there's a number of other suggestions that have been made, but all of them more or less tend to give you a reduction. I mean, they simplify the problem to some extent, but the problem remains NP-hard. That's the general rule. Now, there's another type of approach, which is to use descriptors. Instead of trying to compare the graphs directly, we're going to compute descriptors on each of the graphs, and then we're going to compare the descriptors. Okay? And if we're lucky, first of all, the descriptors will be much easier to compare. And second, the distance between descriptors will be informative. Like, it will give us a good hint of what the actual distance between the graphs is. So this is a line of work that started a few years back. And one of the descriptors that was proposed is related to persistence theory, in particular a branch of it that is called extended persistence. And just to say a few words, basically from a red graph like this one, where the function is the height function, you would get a signature, a descriptor, which has this form. So here you recognize something that looks like a persistence diagram, as Bertrand was presenting earlier. The difference is that you can see that there are also points below the diagonal, and this is the extended part of the process, the extended part of the diagram. Okay, but basically the construction follows the same ideas. So how it goes? How does it go? Well, we will, as earlier, we will look at the sublevel sets of the function. So let's do that. All right. So I'm raising the level. So the gray area is where the sublevel set, the current sublevel set is located. So I'm pouring water and I'm raising the level, and I'm looking at the part of the graph that is immersed in the water. Now, when I reach this level, there's a connected component that appears in the sublevel set. So this creates one feature, which I record here as this point. I know the abscissa, I record the abscissa of this point as being the time when this connected component appears. Now, if I continue the process, there's another component that appears here, and I record it as another feature, and that gives me another point in my diagram. Now I continue, and then at some point there will be another feature that is detected, which is the creation of this hole, and this I see as one coordinate for this particular point. And then as I continue standard persistence, nothing else happens. Okay, so somehow you can see that if you apply ordinary persistence as presented earlier, you will get like half of the information that you have in this diagram. Extended persistence gives you the other half. So how does it do this? Well, the idea is very simple. It's based on duality. It's basically looking at superlevel sets. Okay, if you scan through the superlevel sets, you're going to get the complementary information. And now the theory tells you how to combine the information given from the sublevel sets with the one given from the superlevel sets to merge the two types of information into a single diagram like this one. So how do you read these diagrams? Well, each point here corresponds to a feature of the graph. For instance, this point testifies for the presence of one connected component. This point testifies for the presence of a lower hanging branch. This one for an upper hanging branch. And this one for the presence of a loop. Okay? And there is a dictionary. Let me go back. There is a dictionary between the features that build up the structure of the graph and the points that you have in this diagram. Okay? The diagram won't tell you where each feature is located horizontally, but it will tell you that there are some features, such as connected components, branches, and holes, and it will tell you where they are located vertically, but not horizontally. Okay? So it's not a complete descriptor, but still it gives you some important structural information. So let me move forward. So why is it not a complete descriptor? Before talking about this, the nice property of this descriptor is that it is stable. So namely, if you perturb a little bit your web graph by, for instance, perturbing the domain of the function or perturbing the function itself, then the amount of perturbation of the descriptor will be not more than up to a constant, not more than the amount of perturbation of the graph itself. Okay, so we have this inequality here. The distance between the descriptors is bounded above by a constant times the distance between the graphs. Okay, so you have a descriptor that is stable, which is good. And this way you can get actually, as you can see, you can get a lower bound on the Gromov-Hausdorff distance between the web graphs. So we've answered half of our question. So what is this distance between the descriptors? This is something that Bertrand was mentioning. Well, you can see each descriptor as not as a point cloud, but as a measure, as a discrete measure in the plane. And the natural distance between measures is the Wasserstein distance. It's a matching distance. The problem being that two descriptors may have different total masses, so you have to do something about it, which means that some points may be matched with, not with other points from the other distributions, but with the diagonal, okay? And the cost of an unmatched point is its distance to this diagonal. Okay? But apart from that, it's really the same as a Wasserstein distance. Now, as I said earlier, this descriptor is stable, but not complete. It's not a complete descriptor. So if you give me this diagram, I cannot fully recover the web graph. And here is an example of two web graphs that are not isomorphic, like this one and that one, but which nonetheless have the same signature. Okay? So now the situation is the following. We have this very nice Gromov-Hausdorff distance, which is a true metric between web graphs, which we would like to work with, but which we can't compute exactly or approximate efficiently. And on the other hand, we have this descriptor-based distance, which is weaker because it's only a pseudo distance, but which we can work with. Okay, it's easy to compute. Like the descriptors are easy to compute and to compare. Now, the keystone of this is that there is a connection between the two metrics, or pseudo-metrics, which is that locally this descriptor distance is actually a metric. Like if you fix a rep graph, and if you look at the neighborhood of that rep graph in the topology carried by the Gromov-Hausdorff distance, then in a sufficiently small neighborhood around this rep graph, that particular rep graph can be discriminated from any other rep graph. So the distance to any other rep graph is going to be positive, even in descriptor space. Okay. So this is a very nice connection because now we have like an ideal metric, like our target metric, the Gromov-Hausdorff metric, and we have our tool that we use in practice, this descriptor metric, and we know that the two are more or less equivalent locally. So this raises a lot of interesting questions, such as, well, what if we took the induced intrinsic metrics on the space of rep graphs? The two intrinsic metrics induced by these two would be strongly equivalent. Okay? So this is one of the reasons why it's very interesting to use this descriptor distance in practice, apart from the fact that it's easy to compute. Now, if you want to compute rep graphs in practice, what you would have to do is, well, you start from a point cloud, and you have a filter, a function from that point cloud to R, and you want to do this quotient as I said earlier. The problem is that you don't have access to the underlying space of the point cloud, so you can't really quotient that space. If you start quotienting the point cloud, you'll get just garbage. So we need to do something to recover the original space underlying the point cloud. And so, well, the standard approach is to say, well, we're going to build a simplicial complex on that point cloud, on top of that point cloud. In particular, we're going to build a two-dimensional complex. Why two-dimensional? Well, just because we're interested in graphs. And so to get the rep graph, we just need a two-dimensional complex to start with. We don't need the higher dimensional simplices. Okay? And then we're going to build the rep graph of that simplicial complex equipped with a piecewise linear interpolation of the original function. Okay? Now, the complexity of this process is, well, if you build a complex with m simplices, and if you started with n points, you have a complexity of O, big O of n times m. Okay, in general. In special cases, you can reduce this complexity, but basically this is the standard complexity you will achieve in general. Now, there are two questions. Is this complexity good enough in practice? And do we have convergence? Because you see, we didn't compute the rep graph of the space underlying the data. We computed the rep graph of some complex on the data. Okay, so does that rep graph converges to the one of the underlying space? First question. And second question, is this complexity satisfactory? I can answer the second question immediately and tell you that it is not satisfactory. The reason being that m in practice, because you need the 2D simplicial complex, will be of the order of n to the 3. And so if you multiply by n, you're going to get a complexity in n to the 4. So if you start with like 1,000,000 points, you won't be able to compute this object. Okay? Now, in terms of convergence, there exist results. Assuming that the points are lying on some sufficiently regular space, typically a manifold, with bounded reach. And then you can get convergence under some conditions on the sampling itself. But the conditions are fairly stringent. You have to start with a manifold. And it's not so often in practice that your data are lying close to some manifold. Okay? So because of this, a number of variants have been proposed. Simplifications of the rep graph have been proposed. I'm mentioning a few of them here. And now I'm going to spend the rest of the time on one of them, which is called the mapper, which was introduced in the late 2000s. So what is the idea of the mapper? Well, the mapper can really be viewed as a pixelized version of the rep graph. So you look at your rep graph construction, your quotient, and then you close your eyes a little bit, halfway, and then your singletons here will become intervals. Okay? So instead of taking pre-images of singletons, you're going to take pre-images of intervals. And for each pre-image here, you're going to look at its connected components, and each connected component will give you one node in your graph. Okay? So for this particular interval here, the pre-image contains this tube, this one, and this cap. This gives me 5 connected components, which are shown in magenta here. For the red interval, I get 2 connected components. For the blue interval, I get one connected component. Now, how do I connect these components? Well, whenever 2 intervals overlap, I will look whether their which components of their pre-images overlap. Okay? And this gives me the relationship between the pre-images of the intervals and the pre-images of their intersections. Let me formalize this properly. So from this information, from a space and a function to R, we choose a cover of the codomain of the function, of the image of the function, actually. And then from that cover, we pull it back through the function. So we get a cover of the original space, where each element of the cover is the pre-image of one of the intervals. And now we refine this cover into a connected cover. Each element is path connected. And then we build what we call the nerve of that cover. Okay? So there is one vertex per element in the cover, and there is basically one edge whenever two elements intersect. That's how we get the mapper. In practice, we don't start from the space itself. We start from a point cloud, so we build a neighborhood graph. I didn't draw the neighborhood graph here because otherwise we couldn't read the result. But you have to imagine that every pair of points within this distance here is being connected in the graph. Okay, so we do exactly the same process where we're pulling back this interval on the graph. We're taking their connected components in the graph, and then we're building the nerve of that cover. Okay? If you're lucky, you get the same result as in the continuous case. If you're not lucky, you're not going to get the same result. So this has been used in applications in two ways. The first one is to do clustering, okay, where we're not only interested in gathering points into clusters, but also we're interested in understanding the internal structure of each of the clusters. For instance, you can have a data set where one cluster is this blob here, and another one is this gigantic component here with a lot of structure. And then, hopefully, under some conditions, you will be able to see that structure in your mapper graph. Once again, your mapper graph is a graph, so you can always visualize it in 3D, which is very good for exploration, data exploration. The other way this method has been used is for feature selection. You can see that whenever there's a branch like this or a loop, this branch or loop actually distinguishes a certain subpopulation of your original data. And so this subpopulation, this gives you a hint of which subpopulations may be of interest. So you can do that, you can use this to do, for instance, feature selection, to understand what are the features that discriminate these subpopulations best from the rest of the data. In each of these applications, what mapper has been used for is to detect patterns in the data. Mapper has a certain structure, and we're hoping that this structure is revealing something about the underlying structure of the data. Now, the problem is that when you want to use it in practice, there's a whole bunch of parameters that you have to tune. First and foremost, you have to choose your filter function. Okay? This, I would say, is part of the art of using mapper. So the guy who has been using it for years will be able to tell you for that particular type of data set, you should use this function or that function. Okay? This is not something I'm gonna deal with in the rest of the talk. Just keep in mind that the choice of function will really depend on the type of data. And then there's these other parameters. So there's the neighborhood size for the graph. This is very standard. I mean, data analysis, there's always a choice of scale to be made at some point, and strategies to overcome this. And there's this extra parameter, which is like the most interesting one, which is the choice of the cover of the image of the function. You have to choose the cover. And here there's a lot of freedom. So what people do usually is that they use uniform covers, either uniform in the codomain or uniform in terms of quantiles of the data. Okay. And so when you do this, you have to fix two parameters, which is the granularity of your cover, basically the number of, you can think of it as being the number of intervals you want to use. And there is the gain, what we call the gain, which is the percentage of overlap you're going to take from consecutive intervals. So that's two parameters, R and G. So how hard is it to tune these parameters? Believe me, it's very hard to do it in practice on real data. And most of the papers who have been applying mapper to real data are always silent on this. Okay? They don't say anything about how they tune the parameters. Many of them don't actually give you the magical parameter values. And the very few of them who do so, usually they tell you this. So they did sampling in the space of parameters. So they built millions of graphs, and then, well, they kind of found the ones, a window in parameter space that gave them the most stable results. Okay, that's how they proceed. So that's something we wanted to understand. Here's a simple example. So a point cloud in 2D, so we know exactly what's going on here. And we took two filters. One is a density estimator. The other one is just the x-coordinate function. Okay? And then we did this parameter sampling thing. So if we fix the resolution and gain of the cover and just work with delta, so the window size for the graph, You can see that as the delta increases, the output mapper can have very different structures. And in this particular example, this would be the sweet spot where you're getting what you want to get. But what's interesting is that if you change the filter function, the sweet spot is at a different scale. So that means that the parameters, not only do you have many parameters to tune, but also they are not independent. Okay? So you have to choose to tune them in the right order, which is pretty bad. Now, if I fix the filter and now play around with, and the window, and I play around with the resolution and gain of the cover, here is basically a matrix of results that I get. And as you can see, there can be a lot of noise in the result. Like the result can be fairly unstable. For instance, you see this big loop here, which corresponds to, can I go back? Yeah. Corresponds to this annulus here. So this big loop is mostly present in this region of the parameter space, but sometimes you can see it can disappear suddenly and then reappear. So it's not even, the behavior is not monotonous. So this is very surprising. And also, likewise, there can be like branches that become disconnected and then reconnect themselves again. In a different way, they can create loops and so on. So the behavior is very erratic. And we wanted to have a theory that understands this. So how do we do? Well, we have these rep graphs and their signatures. We want to do the same thing with mappers. Why? Well, because as I said, mappers are just pixelized versions of the rep graphs. So we want to take the signatures for rep graphs and turn them into signatures for mappers. And hopefully these signatures will give us some crucial information about the structure of the mapper. All right, so how do we do this? Well, considering that the mapper is a pixelized version of the rep graph, we start with a rep graph. We build its signature, so this gives us a bunch of points in the plane. So here I have two copies showing different types of points. I won't go into the details. And basically what our theory says is that when you start from this information and you want to get the signature for the mapper, well, because the mapper is kind of a simplified version of the rep graph, well, the signature will be a simplified version of the rep graph signature. How do we simplify it? Well, we remove some of the points in the signature, which means basically that in terms of features, like connected components, branches, or holes, well, in the mapper, there cannot be more such features than in the rep graph, and there can be actually fewer of them. Okay? So how we build, how we select what are the criteria that we use to eliminate some of the features? Well, we build these staircases. The actual definition is not really important, but what's important is that the stairs are actually defined only from the cover. Okay? So if you give me a cover, I can build this staircase, and for every possible choice of rep graph, I can tell you precisely which features of the rep graph will persist in the mapper, and which ones will not. So this way I can build a connection between the two. And in particular, if I have a point such as this one, which would be a loop, as you can see, it's very close to the staircase. You have to imagine being in this situation where the loop is here in the mapper, but the corresponding point in the descriptor is close to the staircase. As I move the parameters a little bit, then suddenly the point enters the staircase, is eliminated, and exactly what happens is that the loop disappears from the mapper. And then as I move further, the point which was eliminated now appears again because it goes out of the staircase, and so the loop appears again. Okay. So we can understand the behavior, like the structure, this result, through our signatures. It also gives us a natural distance between mappers, where it's a matching distance as before, but where points that are not matched are not going to be snapped onto the diagonal, but they're going to be snapped on their staircase, which makes sense. Okay, so we get exactly the same. We get a notion of metric between rep graphs and mappers, and we can speak of the space of rep graphs and mappers as a metric space, and we can ask questions about that space. Okay, here is an example. So the same example as before, but I'm getting into more details. So here is my rep graph. Here is my first choice of cover. Here is the corresponding staircase. Here. And as you can see, for this particular type of point, there's a stair that goes like this. So these 2 points disappear. These 2 points correspond to these 2 loops here. And as you can see in the result, the loops have disappeared. The rest of the points are still there. They're outside the staircase. And indeed, there is still one connected component, one lower hanging branch, and one upper hanging branch. Now, if I change a little bit my cover, then the staircase moves a little bit, like this. And then this point gets caught in the staircase. And this point was for this upward branch. And this upward branch disappears from the mapper. Okay? So this is the notion of distance, as I was mentioning earlier, between mappers and web graphs. And we have this stability result, which follows more or less straightforwardly from the classical stability result for persistence diagrams. And you can extend this to perturbations not only of the function, but of the domain of the function and of the cover as well. Now we have the right tools to mimic what Bertrand was mentioning earlier, to do statistics on persistence diagrams, because now we have a notion of distance between web graphs and mappers that we can work with, and we have stability results. Now these stability results imply that if you start from a measure in that data space and you push it forward to either the web graph space or to the mapper space, both applications here, both maps, are going to be measurable, so you can actually perform the push forward. And you can start doing statistics in that space of web graphs and mapper. And typically the questions we ask ourselves is, well, given this unknown measure and its corresponding web graph, this is our target, this is our ground truth, how far is our estimator mapper computed from data, sampled from the measure, how fast is this guy going to converge to that guy? Okay, can we get some deviation bounds? And the message is that we can basically unfold the same kind of machinery and get, convergence rates that are of the same order as the ones that Bertrand was mentioning, namely log n over n to the 1 over b, where b is basically the intrinsic dimension of the data. So the larger the dimension, the slower the convergence, which is something fairly classical. Okay. Now there's a catch here, because in the difference with like persistence diagrams is that here we have some parameters to tune, and in particular this delta parameter, the window size for the graph, this has to be tuned, and in particular you would need to know the class of measures you're working with to tune it. Typically you would have to assume an A-B standard measure, and you would have to know A and B to tune that parameter, which is pretty bad in practice because we never know what are A and B. And estimating it can be complicated. So there's a trick to it. You basically subsample, as Bertrand was mentioning, and then by subsampling you can get an estimate of that delta n, of that ideal window size. You use this estimate, and then you plug that into the analysis, and then you get a bound that is slightly degraded, but up to polylogarithmic factors. So we're all good. We still have an estimator, namely our mapper here, that is almost minimax optimal up to these log n factors. Okay. And of course, you can iterate this subsampling to get confidence regions. You can use bootstrapping to get confidence regions, as Bertrand was mentioning earlier. So let me take just 1 minute to give a few examples. So in these, let me take this one, which was the example I showed earlier. So for this particular data set, we can get, with our method to tune the parameters, we get this result here, which has almost the right number of connected components, and which, with this big component here that corresponds to this annulus here. And on the diagram, these points have multiplicity too. And as you can see, the connected components that do coincide with what you would consider as being the connected components of the clusters in the original data, they are seen as relevant features because their confidence regions do not touch the diagonal. So we are able, among these output components, we're able to sort between the ones that are relevant and the ones that are not. And this point here, which is also deemed relevant, corresponds to this hole here. Okay. And then I'll stop here. This was just an example. A number of other examples are available. I'll be very happy to talk about them offline. And I thank you for your attention. Let me just mention this list of contributions, and in particular mention this paper, which has just been put up on arXiv and which presents the statistical analysis with Mapper. Thank you very much.